satisfies the system, we know it's true. So once we did all that, we realized that D was the only point that satisfied both of the inequalities. So that's how we got that then. For number 2, you just gotta look at important info. So look at, they give you the 2 inequalities, they give them to you.
Hold on, Mr. Lipham, can we stop? Mr. Lipham is directly going over key ideas for these problems, and I don't see one student taking notes. Come on, y'all. Were you actually taking notes? Because I didn't see you. You were? Okay. Dewan, pick up a pencil.
Oh, I'm gonna wait to do it so I can get credit on it.
No, we're going over it in class right now. You've already got a 0. You got to do it before the time it's due. Take notes now so that you can do this weekend's homework.
Because this stuff will help. So for number 2, let's look at the important info. We noticed the 2 inequalities. And they've already given us this graph right here. We need to see where the solution set is. So for the first inequality, we just test the point and see where we need to shade. And we realize we need to shade below. So we shaded below that inequality. Same with y is b is less than d. We picked the point, it worked, so we had to shade below that boundary line. So whenever we're trying to find where the solutions are, see where you need to shade, test the points, and then once you see where the overlapping shaded region is, that's the answer, that's the solution set. So really the key thing to know here is, if you see solution set, that means it's all the points that make the system true. Alright, so I'm going to give you all a minute to write this down. If you have any quick questions, and then we'll go on to the next one. I'll give you all a second to write these notes. Thank you. So this will definitely help. So if you have any questions, fire away. Yes.
So how do you know D is 0?
I know that D is 0. What do you mean?
Well, how'd you get the 0 plus 17?
Oh, you're talking about right here?
Yeah.
Okay, so all we did here was we were checking a point to see where we needed to shade. So we chose the point 0, 0. So all we did was substitute 0 in for, so this is D right here, and then substituted 0 in for B. So we just substituted 0, 0 in, and we then saw that 0 plus 0 is the same thing as 0, and is 0 less than or equal to 34.
Can you also mark that point on the graph so that you can
Yes.
see that clearly? So I was testing that point. Notice how that point is below the boundary line?
Yeah.
So that point made the inequality true. So that's why I shaded it.
Could you have used any other point instead of 0?
Yeah, you could have. I mean, we're looking at, you can technically use any point on the graph.
Yeah.
I just like to use 0, 0 because it's the easiest mathematically. But you can technically use any point below or above, and if it makes the inequality true, you shade toward below. It doesn't make it true. In this situation, you shade. If you picked one above, it wouldn't make it true. If you picked one below, it wouldn't make it true. So you shade where the point makes it true.
I was yeah, shade where it makes what makes the inequality true. So if it makes the inequality false, then you know to shade to the other side.
Yes.
Alright.
In this situation, we were just shading down. Any other questions? That's a good question. So, for the April 22nd, it's a similar type of problem. We had a system, we needed to graph it and find the solution set. So, graphing these boundary lines, we've been over this a lot, but, slope intercept, you have your slope, you have your intercept, that's how you can graph that this red boundary line. The green one, that's in standard form, so you can either convert it to slope intercept and do it the same way, or find the intercepts, x and y intercepts. So, at x-intercept, y is equal to 0, y-intercept, x is equal to 0. You can use that to substitute it back in and find your intercepts. Once you plot those, that's how you can create your boundary line. Now, for Notice for the first one, we said it was solid because it was greater than or equal to. If it's equal to, it's solid. If it's not equal to, like the second one, it's dashed. That's just a quick detail you can note on there. Yes?
How do we know if we're supposed to shade it down or shade it up?
So that's kind of what we were just talking about. So once we create our boundary lines, then we say, okay, where do we need to shade? So for the first one, we know it's in slope intercept and it's greater than, so we can automatically shade up. Now, if we aren't sure on that, we think maybe we should shade up, we can test a point. So we can test any point technically on the graph, but if we tested a point above this boundary line, it would make the inequality true, and so we'd shade up. Same for the second inequality.
Can you go ahead and show them, let's test 0, 0 on that one, because I think that's a good question, I do want to show you.
So for 0, 0 was tested on the first inequality. So we know that, so we have, I'm just going to rewrite it, so y is greater than or equal to negative 2x plus 4. So now we're going to substitute the point 0, 0. So we know our y is equal to 0 and our x is equal to 0. So is 0 greater than or equal to, that's 0 plus 4, so it's just 4. Is 0 greater than 4?
Nope.
No, so we know it was false, it didn't satisfy. So now we look and we know that 0, 0 is below this boundary line, so we know it's not a solution. So now we shade on the opposite side, we shade above. Now for the second inequality, we can test 0, 0 again. That's perfectly fine, we did that here. We tested 0, 0, and so we have x minus y is greater than 1, or less than 1, sorry. Less than 1, if we test 0, 0 again, is 0 minus 0 less than 1? Or 0 less than 1? Yeah, so it satisfies it, it's true. So now we know that 0, 0, that's above this boundary line, so that's where we shade, is above. So that'll work every time. Every time you test a point and see whether it's true or false and use that to shade, that'll work every single time. Any other questions? That's a really good question. So I'll give y'all a second to write this down, but if there are no other questions, go ahead and pull out your understanding check, because Mr. Kenny's going to continue that conversation of, I think, 4 through 6. Make sure y'all understand your mistakes, and then we will jump into 6.6 for the day. So I'll give y'all just one more minute to write that stuff down, then we'll get into that.
Alright, before we get started, remind me really quickly, did we completely talk about the recursive equation for number 4 yesterday?
No.
We talked about that rate of change and how to write an expression for that rate of change. Okay? For a recursive equation, or writing a recursive equation, what do we typically want to make it easier to write an expression for that linear rate of change?
So,
A table of just what? Do we want to make a table of the quadratic? So a table of just the what?
input in the first difference.
So the input and the rate of change, right? So don't forget that, keep that in mind, right? Big picture ideas, how do we approach this problem? Same idea for when we're thinking about an explicit quadratic. Big picture ideas. And I'm doing this right now and haven't changed the slide so that if anyone needs to copy anything down, they can. But big picture ideas, explicit quadratic, what main ideas should we remember about every explicit quadratic equation? It's got 2 things.
Raised to the power of 2.
Okay. The highest power is the second, right? It is raised to the power of 2. That's probably the biggest one that a lot of students remember, okay? But there's a second one that is also just as important. We learned this when combining linear functions. That was a task, the third one, where we played with the sliders in Desmos. And we took 2 linear functions and we added them, we subtracted them, we multiplied them, and we divided them. Which of those 4 operations created a quadratic? multiplication, okay? So let's check, right? So it seems like we're a little uncertain, which is why I'm going to talk about this. So is that linear? Trey? Is that linear? Not sure. Brooklyn, do you know if that's linear? 2x minus 1? Not sure. Tony? Oh, y'all hurt me now.
I think it is.
Okay, why? What should it remind you of? That doesn't remind you of any, I know it's not an equation, but it doesn't remind you of any equations we've studied?
A quadratic one. It reminded me of the f of x minus 1 thing we did.
Let's say they were,
What type of equation it look like?
I'm asking, is that linear?
Yes.
Why? Oh, it hurt my heart.
And plus subtract one.
So, I mean, what if it was 3x plus 2?
It's still be linear,
Why are both of these linear?
because subtracting is the inverse of addition.
I mean, these are two different expressions. This doesn't remind you of any linear equations that we've studied.
Slope intercept.
Does that look like slope intercept? Does that look like slope intercept? So do we think it might be linear? Hopefully we recognize that now. Those are linear expressions, right? Not equations, but linear expressions. Also, if a quadratic, the highest power is the second, a linear has a power to the first, right? Okay, so these are linear expressions. CJ said multiply them. How do we multiply a binomial times a binomial? We had this in the homework this unit. Distribute, right? 2x needs to be multiplied by what?
3x plus 2.
Yep. And what does negative 1 need to be multiplied by? Or minus 1? Same thing. And so then we distribute all the way out. 2 times 3?
6.
X times x? So I'm not all the way done, but I want you to notice when we multiply two linear expressions, does it give me a quadratic? 6x squared, right? It's quadratic?
Yes.
Based on this definition. So it is the product of two linear expressions. You need to have those notes in your understanding check, because we're about to use them. Those are two fundamental ideas to understanding explicit quadratic equations. So an explicit quadratic, what we know for sure so far is the highest power is the second, so there'll be an x squared somewhere in there, and 2 is the product of two linear expressions. And you can write as two different ways, and we'll explore more about those ideas later, in the next unit actually. Okay? Knowing that there has to be an x squared. Notice how this is figure 1, so that means there needs to be a 1 squared. Figure 2, that means there needs to be a 2 squared, a 3 squared, a 4 squared. Does anyone see a place within the shapes or the figures where we see a 1 squared and a 2 squared and a 3 squared and a 4 squared? Where do you see it, Tony?
Wait, what was the question again?
Is there anywhere within these figures that you already see a 1 squared, a 2 being squared, a 3
Oh, yeah.
squared, and a 4 squared?
The square on the top.
Why do you think it's called a square?
Because it's a square.
Because it's square, right? But when you square something, it's telling me the area of that square. So when I say x squared right here, this is the blocks in each square. Right? But there's a little bit more than just that square there. How much extra is here?
1,
How much extra is here?
2. So would it be 2 squared plus x?
2 squared?
Well,
You mean x squared
x squared
plus...
plus x.
Right. Notice this little tail is always the same as the figure, which is changing, and a variable would take the place of that value. So blocks in the tail. Notice that this method is really useful or easier to see when we're looking at the picture, right? The next method will not be easy to see in the picture, but it will be easier to see in the table. So depending on the representation, we need to be able to see in different ways. The product of 2 linear expressions, right? So what do I need to be thinking about in order to use that second idea, not ID, I don't know what that would come from, but the product, I am what? What is a product? Multiplication, there we go. What can I multiply 1 by to get 2? 2 by to get 6?
3.
3 by to get 12?
4.
Any guesses what the next thing's going to be?
5.
Well, 4 times 5, then
Times 6 times 7.
there's a very clear pattern, isn't it?
Yeah.
Notice how this is always the same as the figure number, so I'm going to just write a variable there, n. How is this number related to the number before it? Like how do I go from 1 to get 2, 2 to get 3, 3 to get 4? So you're saying I'm taking n and I'm adding
Yes.
1 to it?
Mm-hmm.
And what am I doing with these two numbers?
Multiply.
It's a product of 2 linear expressions, isn't it?
Mm-hmm.
Note what happens when I distribute. What's n times n?
N squared
N times 1?
plus n.
Hey, does that match what we have over there?
Yeah.
So 2 very different ways to approach it, but to get C. Do we have those notes? I see us staring a lot, but did we take notes on that so we can use that to help us grow and learn and get better at these skills? Helps have a pencil in hand, Zay, if you're going to take notes. Never mind. You're okay. Don't get better. It's fine. Y'all, an important skill that you need to develop is to not wait on the teacher to say, hey, take a note on this. Yes, you need to think about it, but you got to learn how to think as you're writing. That was a skill I unfortunately did not develop until college. And it bit me in the butt my first semester in college. Mr. Lipham is agreeing.
Yeah, I didn't know how to think that's
I mean, you just reckon. Well,
But the issue is you have to learn how to write as the professor is talking and listen and understand what they're saying as well. That's a skill.
can you write while reading?
nice.
Like,
Yes.
we'll look at something and read it while you're writing.
It's tough.
I can do it.
Good. All right, numbers 5 and 6. We should be a little bit better at these now. Domain. Which of these 4 answer choices can we immediately eliminate because it's asking about domain?
Real numbers.
No.
Yes.
Which ones?
We can eliminate.
Say again.
Output.
Outputs. If we're talking about domain, are we talking about outputs? No, sir. The domain can be the real numbers. The domain cannot be outputs. Domain is only inputs.
Yeah, I know that.
Then why'd you tell me I could eliminate real numbers and not outputs? So what can we eliminate with range? Inputs, right? We're only talking about the outputs. Okay, so now we need to remember what these different numbers, or these different types of numbers are. When we say natural numbers, what do we mean? Okay, so this is very clearly something we need to be taking a note on. You have that pencil ready. Where do we naturally start counting? 1. The whole numbers include 0, but you naturally actually start counting at 1. I have one thing, so 1, 2, 3, 4, 5. Those are my natural numbers. The real numbers are every number that you have currently studied. What kind of numbers are not included in the natural numbers that you have studied?
Would it be a variable?
Decimals.
So a variable is a variable, not a number.
Decimals.
Decimals. What else?
Fractions.
Fractions, which can be converted to decimals. Roots, because I think y'all have talked about square roots maybe. If not, you'll learn about them. Right, so all these different things, when we say negative infinity to infinity, right, those are the real numbers. It's including every decimal, every fraction. It includes 1, 2, 3, 4, and 5, but it also includes all those decimals. So when I look at the domain, the inputs, 1, 2, 3, 4, so on and so forth, are there going to be decimals included in there, or is that just the natural numbers?
Natural.
Just the natural. Same question with the outputs. We see our outputs in the table. Are there any decimals in there, or is it just the natural numbers?
It's gonna be, natural.
Just the natural numbers. There are no decimals involved in those outputs. Any questions on that before Mr. Lipham gets you started back on 6.6? Alright, take us away.
Alright, so going to plot 6.6, we're going to continue what we were working on yesterday.